Okay, so today we're going to conclude the sort of basic tutorial side in the morning, get through latent variables, and the search methods continue to apply to that, and then this afternoon we're going to continue with the breakout sessions. So breakout sessions were okay? Yeah? Different sort of, and bouncing back and forth is, I think, okay and good? Okay, so to give you an outline of what we're going to do, in the section that we're looking at, in which we start with data and then try to get to models, right? We covered bridge principles, deseparation, and the Markov axiom. And then we talked about model equivalence and how deseparation equivalence classes are really what we're searching for these basic algorithms. And then we went into model search, and we went up through what we do on a basic level to search for patterns, which are equivalence classes that only involve, right, the variables you have in your data set, assuming that there are no hidden common causes that you've left out. Right? And today we're going to relax that assumption and allow for hidden common causes. But first, we're going to go back and we're going to do a little bit more in depth about what happens in a search for patterns. And I think what you'll see is that it's, now that you know deseparation like the back of your hand, this will be extremely, I think, helpful in understanding what basically happens in the searches, at least a constraint. And then we're going to do the equivalence classes that include latent variable models. Those are called PAGs, partial ancestral graphs. We're going to do lots of examples when you actually look for models that involve latent variables and see what happens. And then when you have a relative bit of comfort about that, we're going to go back and we're going to compare, right, what happens when you do multiple regression as a tool for doing causal inference versus what happens when you do a model search of the sort that we've been showing you, and what kind of conditions multiple regression is really not the right tool and it's not reliable for what you want to get. And then if we have time, I think we hope we will get to some interesting issues that arise when you have things you're measuring but you don't have measures that don't contain error. So if the measures you have contain error, or if you've taken some quantity and then coarsened it, projected it onto a scale which has many, many fewer values than the thing you're trying to measure, the kind of problems that might arise and what strategies there might be to overcome those problems. Okay? And in the middle of it, during the morning, I'm going to have Joe come up, and maybe Jeremy, and give a few minutes on how to use the command line version of the program that we use and the program that Jeremy is building at CCD. So for any of you who want to actually do more advanced programming work, that's a good session. So we'll try to arrange that so it's right after the morning break. And so for those of you who don't want to see that, you can keep drinking coffee and doing whatever you want to do. Okay? Any questions about where we're going? We're good? Okay. So the first thing I wanted to go back over is you all did searches on those cases which I introduced 2 days ago with real data. And so I wanted to sort of go over what you might have found and what I found with the searches. So I've done the Timberlake and Williams. I've showed you what the search found. But let me go back and show you what I think I got with Tetrad. And you can compare it and comment on whether it's similar to what you got. Okay, so this is the lead and IQ data. So for the lead and IQ case, right, the data is a covariance matrix, a correlation matrix among these variables: how much lead the kid was exposed to, measured by their baby teeth, father's age at birth, the number of live births the mother had prior to the child being tested, the mother's education, the mother's age at the birth of that child, the parent's IQ, and the child's IQ. Right? So that was the basic idea. And the question is, what is the effect of lead on IQ, if any? Right? So I did the search with two kinds of knowledge. Right? One in which I simply, right, let lead be the second tier because it's, right, occurring, right, at a measurement when the child loses their baby teeth that's really prior to anything else happening. I mean after everything else. No, so that's the wrong thing. What am I doing? That was the Oh, and there should be a third tier, which I don't know why that actually happened. So Joe, there's a couple of bugs in the knowledge we've got to look at. What I meant to do here was have 3 tiers, and the third tier would have children's IQ in it. Oh, and there it is. So it was hidden. Okay, so that's what I meant to do. So all the stuff that occurs about the parents, right, that was predating what would happen with the child's lead exposure is in the tier 1, the mother's age of birth, et cetera, and the parent's IQ, et cetera. And then the child's lead exposure is in tier 2, which might be in fact influenced by all the things in tier 1, but couldn't influence them. And then the child's IQ, which wouldn't be able to influence anything else. Now, I should say that in fact, in the history of the lead research and debate, the lead companies who put lead in paint and gasoline were so resistant to the idea that lead might cause damage to a child's developing brain, but acknowledged that there was an association, right, between the amount of lead a child was exposed to and their IQ, and it was a negative association, so more lead exposure, lower IQs, right? They actually tried to argue that the reason for kids who were having a lot of lead exposure, right, was that they were dumber. And that because kids were dumber, they would go and chew on lead paint more often, right, and do things that were going to cause them to ingest more lead, right, and smarter kids would avoid the lead paint. So, you know, this was the argument we got, and that's, that's the way it goes when you have a big financial concern riding on something. Okay, so that's the knowledge, and according to this knowledge, if we execute the FGS search, this is what we get. And in this model, with a penalty discount of the one I did, I don't get any connections to lead, but I get an interesting structure among the other variables. And what it shows us is, according to this search, the only legitimate parents of the child's IQ, right, are the parent's IQ, the mother's education, and the amount of lead exposure. So if we estimate the parameters in this model, right, we might figure out what the effect of lead on IQ is. And you can see that that's a pattern, and then the relationships between the parent's IQ and the father's age of birth, mother's age of birth, right, are unorientable in this particular search. But interestingly enough, right, the parent's IQ, right, is affecting the mother's education, which sort of makes sense, and the number of live births is affecting the mother's education, which also makes sense, right, especially if that's a negative, right, because having more children would prevent you from doing more education. Okay. Now, when we also look at a different kind of knowledge in which I have the same thing, but I also add some required edges, right? in one of them I added the mother's education really would have to affect lead because we really believe that more educated, more efficacious socioeconomic parents avoid the kind of housing that has lots of lead chips in it. So this is a hypothesis that you can put in. And then I also required that the parent's IQ be a direct cause of the child's IQ, which is a completely natural. So under those assumptions,
so what is the gray one and what's the green one?
in the knowledge, the
edges.
right, the gray represents prohibited edges, and the green required edges. And the gray inhibited edges are induced from my tiers of variables. So they're inferred from that tiers of variables. Okay? All right, and so what I got was, right, this model, which is very similar, but just adds this edge. So I'm going to estimate this model, and this is what I get. Right, these arrows are arbitrary, and because there's an interesting, not bug, but a decision we made that I think we'll take back, which was that once these two arrows were oriented arbitrarily, that's why they're yellow, that forces this arrow to go the other way to avoid a collider. So the program says that's not an arbitrary decision any longer, although it's the consequence of an arbitrary decision, so it's still arbitrary. So we're going to fix that so that it will appear yellow also. But the rest of them are blue, and the reason these are oriented into med, anybody can tell me? Why are the arrows from PIQ into med and NLB into med oriented blue? thought you wouldn't have to think, I would have just answered the questions. So it's a collider and it's unshielded. Right. So the PIQ, right, MED and MED NLB, right, are a potential collider, and PIQ and NLB have no adjacency. So they're unshielded. And so we can test to see if that's an arrow collision or not, and it turns out it is. And so we have orientation for both of those arrows into the mother's education, which is actually kind of interesting, and the signs are exactly what you'd expect, right? Parents' IQ seems to have a positive effect on the mother's education, and the number of live births seems to have a negative effect on the mother's education. So that's all what we'd expect. The mother's education tends, according to this, has a negative effect on the lead that the child is exposed to. That makes perfect sense. Parents' IQ is positive into child's IQ. That makes sense. The mother's education is positive into child's IQ. That makes sense. And the lead into children's IQ is negative. And if I look at the p-value for this, it's 0.0028. So if the rest of the model is structurally accurate, then this coefficient inference, right, says that this really is statistically not by chance and something real. Okay? So anybody get anything radically different than this? I used FGS. Now, if you use different search algorithms, you will get different results and different knowledge. Sorry? FGS is usually my go-to. It's fast, and it's a score-based search, and so with small sample, yeah, I think it tends to be more accurate. Okay, so if anybody got anything different, it would be interesting to show me or send me the tetrad file and we can compare. But there's two ways in which the thing might be different. One way is that it's structurally different with the edges, but the more important way is that it has really different scientific conclusions. Right? So if you have different structure, but the effect that lead still has an effect on CIQ and it's still estimated to be negative in approximately that ballpark, right, then we might disagree about parts of the model, but we agree about that part. And that's another piece of evidence, I think, that that conclusion at least stands up to or is robust against different kinds of assumptions. All right, so that's the lead and IQ case. And this is real data from 1979 taken from Herb Needleman's landmark study of Boston area children. And in fact, I think even though at the time this was incredibly revolutionary data and very, very controversial, now lead is accepted because there's been thousands of studies as doing real damage to the child's developing brain. And many people have argued that you can trace the effects of lead, right, into the crime rate, into delinquency, into all sorts of other problems with ADHD, et cetera, et cetera. So when I was a kid, there was an awful lot of lead in the air from gasoline and a lot of lead in paint. And so the lead that's in the air and in the paint now is so much less than it was that I think things are much, much better. Okay, so that's the lead case. And let me go to the charity case next. So the charity case, did anybody find a model that fit the data? That had a p-value for model fit above 0.05? Yeah?
Can I ask a question about the lead case?
Sure.
How was it modeled in the original paper?
So the original paper was all regression. And in the regression, right, the lead was taken to be the output. I mean, CIQ was the output. And everybody else was taken to be the input, right? And in that, you had a negative 0.15, right, and it was significant at 0.01, right? So now the coefficient is negative 0.17, significant at about the same level. So this underestimated the effect of lead.
Would it be reasonable to use the causal graph to inform the variable selection for the regression?
Completely. So if I do the same regression, but I only use the direct parents of tetrad, I should get the same result that I got in tetrad. So let's try that, right? So I got to take this out, I got to take this out, got to take this out. So those are the only three that tetrad says, and if I execute that, right, I'll get the same numbers I got in tetrad. And that's exactly the way the estimation works. Yeah. So you can do a causal search, right? And a more sophisticated way to think about it is do a search for the Markov blanket and then use just the Markov blanket in the regression.
But the Markov blanket includes children, doesn't it?
Yes. So you don't want to use that for regression. Yeah, so you're right. So you just want to use the parents, right, if you can locate who are the parents. Sorry, I misspoke. Good. Any other questions on lead? Okay. So here is the, no, that's still the lead. Okay. So did anybody find a model? I mean, so when we estimated the model that the theorists gave us, right, the fit was terrible. It was rejectable at 0.00000000. And then the question was, is there a model, right, that makes sense theoretically that fits the data? So we estimated, or we searched under the assumption that the experimental condition was exogenous, right? And we should represent that by, so here was the model we first fit. Right, that doesn't fit the data at all. And then we did a search with nothing. I won't go into that. And in this, right, we have 3 tiers. We have the tangibility condition in tier 1, which represents it's exogenous because it was experimentally manipulated and randomized. Then we have all these guys in tier 2, and this was in tier 3, and there's a bug here too. Right. Right, so that's the bug, and I don't know why that is. Okay, but this is the model that I get, right, which is fully oriented because of this guy, which is kind of interesting, right? So since tangibility is exogenous, right, this connection has to be oriented, and because this is a non-collider, that orients this, and then because this is a non-collider, it orients this, and this is so everything gets oriented by that one decision, that one assumption about tangibility being exogenous. But you'll notice that according to this model, the influence of the experiment went through one's attitude, sympathy, and then impact, but imaginability was an epiphenomenon. It didn't really have anything to do causally, right, with the outcome. But what we can see is that if there's anything proximate that's causing amount donated, it's how much impact you think you're going to have, right? And if I look at that and I say, what's the estimated numbers, right, I get a more tangible scenario causes sympathy, sympathy causes impact, and impact causes amount donated. And the model statistics are very good. The p-value is 0.38. That model fits the data quite well, right? So we have at least found a model that fits the data, which allows us to say if there's any evidence from the data about what's causing what, right, it's at least contained in some model that we know fits. Okay, and then I did a search in which I had the same pattern, but I had also the required edge that tangibility has to be a direct cause of imaginability, which is a controversial assumption, but one that the theorists actually insisted upon. So when I save that and I do the search, right, what I get out is a little different. Now, tangibility causes imaginability, which is the assumption, right? It also causes sympathy. But now, sympathy is a detectable collider because of the different structure, and this guy, right, contains the flow of impact through impact. That's a redundant way. So the causal influence of the condition on amount donated doesn't go through sympathy. That's the epiphenomenal. It goes through impact. So I think this is a nice example. Oh, let me show you how this estimates too. Okay, so there's the estimate, and the p-value here is 0.26. So that fits the data also. It's, both p-values are above 0.05. They both fit the data, right? And it then comes down to how seriously you want to take the assumption that the tangibility is a direct cause of imaginability, right? But here's what I want to point out, that in both of these models, right, this is the one where tangibility causes Right, and this is the other one. No, that's not the other one. This is the other one. In both of these models, right, if I said to you, we don't know which of these models is true, what would you take away from this analysis? As a scientist. So you're now being consulted, and the question being posed to you is, how do I get people to donate more money to my charity?
It seems that the only direct cause of the amount donated is the impact, the
Yes.
perceived impact.
It's impact, and they both agree on that.
And they both agree on that.
Right, and the estimated quantity is the same because that's the only parent. So I really think that's the takeaway message from this data set, right? It's uncertain what sympathy does, right? And whatever sympathy does, it seems to be screened off by impact. So if you're going to try to actually get people to donate more, you're better off manipulating how much impact they think they're going to have, right? Or they really will have, right? As opposed to making them sympathetic with your, right, your target. Okay? So I mean, I think this was published, and there's a real conclusion here causally, and it's interesting. And I think that it's very difficult to know what to do in these kind of cases when we have different models, different things coming out with different assumptions. But I think it's a good heuristic to say, look, if there's something common, right, that is in every model you look at, every model you output, that's stable across those different assumptions, then, right, that ought to be a more reliable thing you can conclude than things that switch a lot sensitively to different assumptions. And in this case, it's that impact is the key guy. Okay? Any questions on that? Any questions on those searches? Everybody had reasonable success doing this? Okay, good.
Would you be talking about the different variants of PC or
The different variables of what?
different variants of the PC search?
I was not planning to talk about that. If you want, we can do. That's a pretty sophisticated technique. I mean, there's
Pointers to it somewhere?
yeah, in the Tetrad program, and Joe, you could confirm this for me, right? There's a manual that we can get to, right? And there's a help system, which Joe can maybe show you later, in which we document all those different algorithms and say what they're about and there's references to them in the literature. Okay. Okay, so now I want to back up and take a step back and sort of go into a little more depth about what's happening underneath the hood when we do these constraint-based searches, right? Because that sort of connects the deseparation theory to what's going on underneath. So we do the searches in two phases. First, right, we don't worry about the directions of the arrows. We try to get the adjacencies. What's the skeleton that's undirected? And once we have that figured out, we then move to, can we orient the edges, right, and find out which way the direction of the arrows might point. Now, we've done an awful lot of simulation studies, an awful lot of cases, and I think one of the things that I think we believe is that the adjacency phase, right, is more reliable, right, and easier to have confidence in than the orientation phase. Right? So it's often the case that we're very accurate on an adjacency search, but the orientation part of the search is not as accurate. Okay, so how do we do adjacency? Well, there's this beautiful little theorem that says, right, if you have two variables, x and y, they can't be adjacent if they're independent on any subset. So if there's any subset that deseparates or make them independent, right, then they're not adjacent in the graph that generated the data. So what that says is, right, any way you can separate two guys is good enough. You don't have to keep looking. As soon as you find someone, right, that's a separating set for x and y, you can remove the adjacency and then continue looking for other adjacencies. So what we do is we begin with a fully connected undirected graph where everybody's connected to everybody else. Then we remove the adjacency x and y if there's independence in the data x and y conditional on any set. And what we do with those any sets, right, is we start out with nothing in that set, so our x and y independent conditional on nothing. And then if they still are dependent, right, we look at all the sets of size 1. And then if they're still dependent, we look at all the sets of size 2, with even extra caveat that we only look at variables for those sets, right, that are themselves adjacent to either x or y, because no other variable could separate them in the graph. So it's extremely important, right, to the efficiency of the search to be very systematic about selecting only the tests one needs to do in order to keep going. That very efficiency, because you're only going to do the minimum number of tests, and the tests that you do early determine the tests you do later, right, will also lead to errors later that you can't recover from, because you don't even do the test you need to do to recover. Okay, so here's an example. So suppose that this graph on the top is the true graph, right? We call this the Y structure. It's like a sideways Y. And we know from d-separation that the independencies entailed to hold in any way to parameterize this graph are shown here. x1 is independent of x2, and x1 and x4 are independent on x3. It's, right, a non-collider on the only path. And x2 is independent of x4, conditional on x3. It's a non-collider on the only path. So that's it. It's those three independencies, and no other independencies are entailed. And if we assume faithfulness, then no other independencies will be visible in the data, right? Okay, so we begin with everybody connected to everybody else, and we look through all the zero-order independencies, all the pairs of variables conditioned on nobody, and we see that x1 and x2 are independent because that's one of the zero-order independencies and the only zero-order independence. And from that, we actually remove the x1, x2 adjacency. And then we get the first-order adjacency searches, and when we're looking at x1, x4, right, we don't have to consider, right, everybody if they're not adjacent, but it turns out that x3 is adjacent to both. We have to consider it. x2 is adjacent to x4, right, so we still consider it. And we get x1 and x4 are independent on x3, so we take away that edge. And we do the same thing for x2, x4, right? We do not any longer have to consider x1, right, because it's not adjacent to either one. So we only consider x3, and then x2 and x4 are independent on x3, so we take away that adjacency as well. So that's the end of the adjacency phase, and we got just the right adjacencies. Right? It's very simple. Yeah?
What test is being used to determine if they're independent or not?
So in this presentation, it's just independence. But in the actual algorithms, if you have continuous data, right, we use partial correlations and z-scores and tests, right, to test independence in that case. And if it's a discrete variable model, right, we use a variant of the chi-square test, which is called the g-squared test. Right? But I should mention that there's a way, if you want to do independence tests on your own, right, and then enter the independence tests as the input to the algorithm, you can do that. Right? And so if your data are a little strange or that you want to use particular tests, right, for the data you have, you can do that and then give them to the algorithm, and it will just take as input the independence facts, which is really all it cares about. Okay, so now we finished the adjacency phase. Now it's like, what do we do in the orientation phase? How do we orient these things? Well, the first thing we do is called the collider test. We first look for triples, right, x, y, z, so that we have x adjacent to y, y adjacent to z, but x and z not adjacent. So those triples are called potential colliders, right? And then we actually look to see if the set that separated x and z, if something had to separate x and z if they're no longer adjacent, contains that middle guy y. And I'm going to show that in a little more detail in a minute. But that's the key to actually orienting that. Once we have the triple and the x and z are not adjacent, something made them go away, that adjacency go away, the question is, what was the separating set that made them go away? Did it contain y or did it not contain y? That's the key question. And then there's this other test that's just incredibly beautiful and powerful, my favorite test, orientation, the away from collider test, which I'll explain in a little bit of a detail. And then we repeat that until there are no four orientations, and then there are these other rules I won't go into that Chris Meek came up with that make all the orientations one could possibly get out of there So we know these rules are complete. There is no more information that is to be had from independence. All right, and then that's all we do. But I'm not going to go into the meek rules, but that's an interesting topic if anybody's interested in and of itself. Okay, so let's just go through that. Why can we do the orientation from these triples? Okay, so we have Y as unshielded, as a potential collider or a non-collider. And as you recall from that theorem, right, graphs are equivalent. They have to have the same set of unshielded colliders, right? So if this is unshielded, right, we must be able to tell whether it's a non-collider or a collider. What is the test? We test to see when X was independent of Z, right, by the set S, something had to do it, whether Y is an element of the set. Now see if you can guess ahead of time, right, what we would do if that set S did not contain Y. How do we orient that triple? Or alternatively, if you want to guess, suppose Y is in that set. So let's just suppose for a second that Y is a collider between X and Z. X is adjacent to Y is adjacent to Z, and Y is a collider. Right? What would happen if we condition on a set that included Y? Sorry, what?
They become dependent.
X and Z become dependent. We activate the collider, they become dependent, and therefore they would not be found to be independent, right? So if it turns out that Y is not in the set, right, it's a collider. Because if it was in the set as a collider, if it was in the set, it could not be a collider. I mean, that's just the easy thing. And if it was yes, Y is in the set, then it must be a non-collider, right? Because if it was a non-collider and we failed the condition on it, it remains dependent because now there's a path through the non-collider that we did not deactivate. So the non-collider starts as an active thing, and unless we condition on it and deactivate it, it will carry association, right? So it's got to be a non-collider if it was in the set. So that's the simple test. You just look to see whatever set you found, right, whether it contains Y. If it did, right, it's a non-collider. If it didn't, it's a collider. It's as simple as that. Okay, and if it's a non-collider, of course, this is the actual structure we sort of think that this is a non-collider on this path, right? And that's the outcome of that test. And then we have this extra rule in which we've gone through and we've oriented some of the edges, but not all of them. We might find now a triple, right, in which one of those edges in the triple, right, was oriented from some other test involving some other variable down here, right? And so x1 and x2 has been oriented by that collider test, but x2 and x3 was not oriented. Well, now you look at this and now you say, gee, right, if we know that x2 is a collider, right, then we can orient it this way, but it probably was the case that it was a non-collider, or we would have oriented it anyway. Right, so if x2 is in the set, right, then it would have to be a non-collider. So if it's in the set, if it's not in the set, it has to be a collider, so we can orient it that way. But if it's, right, if it's in the set, which means it's a non-collider, then we don't have to actually stay away from the orientation. We can orient it fully. Because if it was oriented the other way, if x3 was causing x2, right, it's a collider. We know it's a non-collider, so there's only one thing left to do, which is to orient x2 and x3 away from the x2 collider. So that's a and that turns out to be very powerful, especially in the latent variable case, which I'll come back to in a second. Okay, everybody good for that? That was a little incoherent, but I think I got the message across. Okay, so after the adjacency phase, let's go through what happens in this model. Right? In this model, I start out with the adjacencies there, and I do a collider test on 1, 3, 2, which is this triple there, right? And I see that x1 and x2 are independent, right? So it does not involve x3 in the separating set. And so I orient that into X3 as a collider. Okay? Now I have to say, what are my triples that remain? And I have two of them. I have the 1, 3, 4 triple, and I have the 2, 3, 4 triple. And that's it. And in both of those cases, I'm set up for the away from collider test or the collider test, and I ask the question, right, is X3 in the separating set for the 1, 4 and the 2, 4? And the answer is yes to both, and so I get to orient, right, this edge as an away from collider and make it go from X3 to X4. So I've obviously chosen this case because everything gets oriented, and it's nice to see that, right? And in some cases, nothing gets oriented, right? But in some cases, you're lucky. And this structure is special. Right? This is a special structure, and I'll get back to what's special about it in just a few minutes. Okay, so when I actually have that kind of condition, right, I get that, right, result, and I have a question for you that sort of goes to the heart of the problem when we're actually allowing confounders. Why does this test also show that X2 and X3 are unconfounded, which is to say there is no common cause between them that I've left out of the model or that left out of the data analysis? Why would that be the case? So this is the picture of what it would be for them to be confounded where C is unmeasured. So why does this test eliminate that as a possibility?
We discussed it yesterday by an example. This is in K. If there is a C, then the C is the alternative pathway, and if there is this independence is shown here, then there is no alternative pathway.
That's in the right direction, not exactly, but you're close. Anybody else? I'm sorry, say it again. That's correct. So there's two paths now, right? There's the path here, right? And there's the path here. And so if this was the truth, right, what would we see? We would not be able to separate X1 and X3 by any set that did not include, right, C, because if we put X, we have to put X2 in there because this is an active path otherwise. And the moment we put X2 in, we activate this path. We can't condition on that. So X1 and X3 could not be separated at all, right? Because basically, that induces, there is a collider now between X1 and X3, and that's not even measured on that path. So we wouldn't be able to separate them at all. So the away from collider, we don't know that X1 and X2 are unconfounded, but since we oriented this as an away from collider, we do know that X2 and X3 are unconfounded. That's a very powerful conclusion, right? It's saying that there does not exist some latent common cause you've left out of the model. Okay, so that's the explanation. I'll go on. Okay, any questions so far? That's as much as I'm going to say, yeah.
Does the order matter when you test one? Go back 2 slides. Yeah. So you first do the triplets X1, X3, and X2, and you do another one. Does it matter if I do X2, X3, 4 first?
It wouldn't matter in the end because the algorithm says keep repeating until there's no information left to actually gain. So if you did it the other way first, if I did these guys first, right, I'd get that's a non-collider on this path and that's a non-collider on this path. And then I'd be faced with that information. But then when I went back to look at the X1, 3, X2, I'd see that these are oriented, and I'd revisit again to see if I have an away from collider test. I would. So it'd take me longer to get there, but I'd get there. And the algorithm just iterates. Now, if it turns out these are all assuming that my statistical decisions about independence are made correctly. But if they're not made correctly, right, at some earlier stage, then I could screw myself up big time. And that happens. I mean, there's just no doubt about it. So in some cases, right, if I do some order of tests, and some of the early tests come out, right, just statistically, right, incorrect, then I won't even do the tests I need to later on in some cases, which is another reason why the scoring-based search, right, is a little bit more reliable, because it doesn't have that problem. Right? It looks at all the tests simultaneously for the whole model and judges them jointly. Yeah?
What's an example of this particular constraint-based search?
Screwing up? Or
No, in constraint-based search, what is an example of an algorithm that does this?
oh, I'm sorry, the PC algorithm and all the variants are all constraint-based search. And so is the FCI algorithm, which I'll get to in a minute. And in some sense, the score-based search, right, is preferable in models in which you don't think you have any confounding. But in models you do suspect you have some confounding, you really usually can't do a score-based search. I'll get to that in a minute. So you have to do a constraint-based search. So that's, sorry, the PC algorithm is the classic, right, and all the variants of it. I can give you one quick example, right, of one of the variants of the PC that's called PC conservative, right? So if I have a triple, right, like that, there's only two possibilities that ought to happen, right? One, it's a collider, and the other, it's a non-collider. So suppose those are the only three variables I'm looking at. This should say x is independent of z, and it should say that x is independent of z given y is untrue, not true. So those are the two constraints, right, that I ought to observe about x and z if this is the true model. And in this model, it's the opposite. Okay? Now, what happens if statistically, right, I look and they both come out true? Though there is no model. That can happen. That can happen if this is the true structure, if these are both weak. Because in a non-collider situation, the correlation or the association between x and z is in some sense, in a linear model at least, it's the product of this association times this association. And so even though this model says that this is associated, and these are also associated, right? If this is weak and this is weak, right, they might look statistically like they're not associated just because it's pretty weak, right? And we'd make the wrong decision, right? So this is the correct decision, because it really does screen off x and z and make their association 0. But this is the incorrect decision because it just turns out to be too weak an association at a small sample size to tell us, right, what's going on. So in that case, we withhold any orientation. We don't do any orientation. We say, we don't know, right? And then we move on. So there's sort of versions of the algorithm which we don't do the most aggressive orientation, right, if we have some information that tells us we don't really know what's going on here, right? There's inconsistent information. And PC conservative is one of the ones that does that. Okay. Okay, so then that brings me to the next topic, which is, okay, so what do I do now if I'm really looking for models and I'm willing to admit that I might have only measured certain of the variables and the common causes that I didn't measure are still out there lurking, and I want to deal with them? Well, we do have this beautiful theory about that, and it's really based on partial ancestral graphs, which are a way to represent, right, the deseparation equivalence class that includes models of latent common causes that I've left out, and sample selection bias, which I'm not going to talk about. And what you're looking for now is a set of models, right, that are deseparation equivalent over the variables you've measured, right? So if nothing you could measure could tell these two models apart, right, then they're deseparation equivalent over the measured variables. And that's kind of the key idea. Okay, so what's a PAG look like? Well, now it involves these circles, right, and these arrows. And the circles, in some intuitive sense, represent ignorance. We don't really know what's going on that side of the adjacency. So now the adjacency really can be conceived of, where did I put it? So if it's no confounders, right, what are the possibilities? It's either that, or that, right? If it's including latent common causes, then that's a possibility, or this variable up there that I haven't put any value or name to, right, is some other common cause I haven't measured, right? That's another possibility, right? That's a possibility, right? Et cetera, et cetera. So if I allow cycles, there's the two causes. But even if I don't allow these, and I just allow these, you can see that if I'm looking at an adjacency, right, in this case, right, either there's an arrow on one side or the other, but it can't be on both. But in this case, it could be on both. And so that edge with a circle on both sides is the representation of total uncertainty about the orientation. We don't know what's going on this side of the arrowhead. We don't know what's going on that side of the arrowhead. So this represents could be out of or into. And this represents could be out of or into. Okay? Or even both. So if I look up there and I say, okay, this is the partial ancestral graph that represents an equivalence class. What is the equivalence class? Well, intuitively, it represents all the models with these adjacencies, right, that have arrowheads that go into X3, but might vary about the arrowheads coming out of or into X1, and it might vary about the arrowheads that go out of or into X2. Okay? So what are those models? Well, some of them are pictured here. Right, so there's the simplest one without any latent common causes. Right? The arrowheads go into X3 and they come out of X1 and out of X2. Here's a model in which, right, both of the arrowheads go into X3, one of the arrows comes out of X2 and the other goes into X1. Right? Here they both go into X1 and X2, and here's the other way. And there's, in some sense, an infinity of these models, because when we say there's a latent variable here, we only list one latent variable, but there could be two, could be three, could be 1,000, a million. So there's really an infinity class, and what everything in this class shares, right, can be summarized by these adjacencies and saying that X3 is not a causal ancestor of X1, and it's not a causal ancestor of X2. So the conclusions are in some sense more precisely stated in the negative. Right? The arrowheads say what is not happening. Right? It doesn't say that there might be a cause. Actually, it does say there might be a cause, but there is no cause from X3 to X1. Okay, and this now takes me back to the Y structure I gave you before, which is a really interesting case. So there's the PAG that represents the Y structure, and you'll notice that the connections between Z1 and X and Z2 and X, right, are different than the connections between X and Y. And every member of the equivalence class, right, the XY is a directed edge with no confounding. Right, there, 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 there. So that's, right, completely uniform over all the members of the equivalence class, but what varies, right, are the Z1X and Z2X connections, and the PAG I showed you on the previous slide is sort of the same PAG that connects these three variables here. So it could be this way, it could be this way, it could be this way, et cetera, et cetera. But in every one of those models, x3 is an unconfounded direct cause of y. Which is kind of cool. Okay, so what the edges in a PAG mean are a little disappointing, right? I have to warn you, I'm still not getting over this, even though this is now more than 20 years ago that this was discovered. When there's no adjacency, it means that you think there's no adjacency in the real graph, or any graph. And when this happens, you would think that it would mean something like there's an adjacency, but it really doesn't. It means x2 is not an ancestor of x1. And this is the key uncertainty. If there's this edge, all it means is that no set d-separates them. It doesn't even mean they're adjacent in the real graph. And I'll get to the example that shows that in a few minutes. This one is a happy thing. It means that really x1 is the direct cause of x2 relative to these variables in every graph that's equivalent in this set. And then this one's actually pretty cool. If you have a double-headed arrow like this, it means there really is some latent common cause of x2 that has been left out of the variables you've measured. So that's very informative. So these last two are very informative, right? That's kind of informative, and these are kind of disappointingly uninformative. The orientation, right, that we do for PAGs is exactly what you'd think it would be. It's the same, except now it's only on one side of the edge. So if we see this triple, right, after the adjacency phase, which is the same, we do the same test. What was it that actually separated x and z? And did it include y? If it did not include y, right, so if y are dependent when you put it in the set, then y has to be a collider, and we orient this side of the edge in both cases, but not this side. So we leave those circles there. And that represents, we don't know what's happening on that side of the edge. We do know that whatever the connections are between z and y and x and y, right, the arrowheads are into y. So that's all we know from that test. And in the other one, we know that whatever the connections are, the arrowheads do not collide at y. Okay, so if we do the same exact example that we had before, and now with latent variables as a possibility in mind, right, this is what we get after the adjacency phase. It's, right, those circle uncertainties. We do a collider test for 1, 3, 2. We find that 1 is, right, independent of 2, and so we orient this guy into there. But we do not orient the x1 side of that edge or the x2 side of that edge. We leave that uncertain. Makes sense, yeah? And then when we do the away from collider test, right, because we have the 1, 3, 4 and the 2, 3, 4 triples, right, we find the independence goes, and now, right, we can orient that side of the edge and that side of the edge. Because if this side of the edge was an arrow pointing into x3, it would be a detectable unshielded collider in both cases. It's not. We can therefore orient it as out of x3. So that's an unconfounded direct cause of x3 to x4. So that's the power of the away from collider test, even in the presence of latent variables. Cool? Everybody good? Yeah? Okay. So now there's a bunch of interesting cases I want to go through, and I want you to go through with the program to see what's going on. I'm going to demo, right, one of them and then leave it up to you guys to explore the others. Right? And these are all interesting cases. Right? Okay, so L in this case, and any variable that's got a circle around it, is to be considered a latent variable, which is not going to have, right, anything measured in the data you look at. So we have to actually model it as a latent variable. It will not act any differently under the hood as the other variables that are measured. It just, you won't see data on it. That's the only thing we mean when we say a variable is latent. All right. So what I'm going to ask you to do then, right, is create for each of these things a new session, right, and then make a search from simulated data template and then see what happens. And I'm going to demonstrate for the first one so you can see what I'm doing. And I'll go back to that slide, just put it up there. Okay, so open a new session, and then go to the template menu and say, search from simulated data. And then you get the boxes you need. And then I go into the graph and I say, find directed acyclic graph. And now I'm going to build a model in which x1 is the cause of x2 is the cause of x3, and then I click on this latent guy and make it a common cause of 2 and 3. Okay, so that's my model. That's the truth, and I parameterize it, and it doesn't matter how I parameterize it. All this will do the same in any case. Right? Save, and I get 1,000 data points. And now, when I do the search, right, let's first do a pattern search to see what happens. So if I do a PC search, or let's do an FGS search, right, I just get the complete graph. Even if I put them in the positions that they were in, roughly, right, I get that. But now let's do another search, right, where I allow for the possibility of latent common causes. And so in that case, I'm looking at what's called a PAG search, partial ancestral graph search. And there's several of them. This is the fast causal inference. This is the conservative fast causal inference. What does G stand for?
Greedy.
Greedy fast causal inference. And I'll just do regular FCI here, right? It's just like the PC. You have to pick an alpha value and a depth, right? And if I execute it, what I get is manifestly disappointing. Okay, so what am I getting here? Right? What I'm getting is that x1 and x2 are adjacent like they are in the real graph. x2 and x3 are adjacent like they are in the real graph. But x1 and x3 are not adjacent to the real graph. Right? There's a latent common cause of 2 and 3. And that latent common cause makes it impossible to separate x1 and x3 if all I measure is x2. And so the fact that they're connected means very little causally. And that's what's disappointing. Got it? Clear? Okay, yeah.
Can you go back to your directed acyclic graph for this? What was it like, Chief?
Can I go back to the graph? So I'm sorry, so here's the graph. And there's the output of the FCI algorithm. And so it's really not very informative. What I'm getting is an output in a certain way. But that's the fact of the matter. That's all that can be learned about the structure among x1, x2, and x3 if all I have access to is independence relationships, right, and nothing else. No interventions, etc. All right, I'll do one more, and then I'll leave you guys to do the other. Now suppose I do something a little interesting. So now I say that x1 is a direct cause of x3, x2 is a direct cause of x4, but x3 and x4 are related because there's a common cause that's L1, that's a latent variable that's in between them. Okay, I only have 4 variables measured. Let me show you that again. There is no L1 out there. It's just 1 through 4. And now if I apply the FCI algorithm, what I get is that. So in this case, I can't tell what's happening between x1 and x3. All I know is that x3 is not an ancestor of x1. Same thing for x2 and x4. I know x1 and x2 aren't adjacent, and x1, x4, x2 and x3 aren't adjacent. But I do know between x3 and x4 that there's a latent common cause I've left out. Right? So this is one of these examples where you can actually learn a lot, right, that you couldn't learn it any other way. So the circle between x1 and x3 means we don't know what's happening on that side of the edge. Could be out of, could be into. So right there It might be that the connection is out of x3, out of x1, toward x3, or it might be into. So you can see here it's into x3, here it's into x4. Here it's into x3, don't know. Into x4, don't know. That's the idea. We don't know the orientation on that side of the edge. And so the generalization to latents, you have to take both sides of the edge separately now as opposed to the holistic edge. And that's the big difference.
If you introduce a new latent variable between the x1 and x3, what happens?
You get the same output. And that's another interesting case. So that's an interesting case I want you to do. So in some cases, the latent variable is detectable, right? And in some cases, it's not. And that's, you know, one of the things. So you have to be lucky and good to get the information that you really want. Okay. So let me now turn it over to you guys, so you can learn how to do these searches with latent variables. And we will walk around and help you, and we will regather. So here are the three cases. So I've done this case for you, right? And here's another case I want you to do. And this is a third case I want you to do, and we're going to do a fourth later on. So do a template where you search for simulated data, build the graphs, parameterize, instantiate, and generate sample data. And make it big enough so that the statistics don't get in the way. And then execute a PC search and an FCI search. See what happens. Compare the output you get both to each other and to the true model. Good, and we'll walk around and help. And then when you're finished, take a break. We'll regather at 10:30. Good? Everybody clear? Any questions before we go and walk around and just let you guys loose? Fantastic. Okay, and I'll leave this up there.